Bernoulli's principle was discovered by the Swiss mathematician and physicist Daniel Bernoulli, who published it in his 1738 book Hydrodynamica, establishing the relationship between fluid speed, pressure, and potential energy. Though Leonhard Euler later derived the principle into its modern equation form in 1752, Bernoulli's theorem, or principle, states that for an ideal fluid in steady flow, the total mechanical energy along a streamline is constant, meaning an increase in fluid speed occurs with a decrease in pressure or potential energy, height, and vice versa, described by the equation pressure energy plus kinetic energy plus potential energy equals constant. Bernoulli's principle is a key concept in fluid dynamics that relates pressure, speed, and height. For example, for a fluid flowing horizontally, Bernoulli's principle states that an increase in the speed occurs simultaneously with a decrease in pressure. Bernoulli's principle can be derived from the principle of conservation of energy. This states that, in a steady flow, the sum of all forms of energy in a fluid is the same at all points that are free of viscous forces. This requires that the sum of kinetic energy, potential energy, and internal energy remains constant. Thus, an increase in the speed of the fluid, implying an increase in its kinetic energy, occurs with a simultaneous decrease in the sum of its potential energy, including the static pressure, and internal energy. If the fluid is flowing out of a reservoir, the sum of all forms of energy is the same because, in a reservoir, the energy per unit volume, the sum of pressure and gravitational potential ρgh, is the same everywhere. Bernoulli's equation and the Bernoulli constant are applicable throughout any region of flow where the energy per unit mass is uniform. Because the energy per unit mass of liquid in a well-mixed reservoir is uniform throughout, Bernoulli's equation can be used to analyze the fluid flow everywhere in that reservoir, including pipes or flow fields that the reservoir feeds. The following assumptions must be met for this Bernoulli equation to apply. The flow must be steady. That is, the flow parameters, velocity, density, etc., at any point cannot change with time. The flow must be incompressible, even though pressure varies. The density must remain constant along a streamline. Friction by viscous forces must be negligible. Key examples of Bernoulli's principle. Airplane wings. The shape of an airplane wing, airfoil, is designed so that air moves faster over the top surface than underneath. This difference in airflow speed creates lower pressure above the wing and higher pressure below, generating lift that allows the airplane to fly. Carburetors. In older car engines, carburetors utilize Bernoulli's principle to mix air and fuel. As air flows through a narrow section of the carburetor, the venturi, its speed increases, causing a drop in pressure that draws fuel into the airflow, creating the necessary mixture for combustion. Shower curtain effect. When taking a hot shower, the steam and fast-moving air create a low-pressure area between you and the shower curtain. The higher pressure outside the curtain pushes it inward, causing it to cling to you. Venturi effect. This principle is used in various applications, such as in venturi meters, which measure fluid flow. As fluid passes through a constricted section of a pipe, its velocity increases, leading to a decrease in pressure, which can be used to calculate flow rates. Kites. When a kite flies, the shape of the kite and the angle at which it is held create differences in airspeed above and below the surface. This results in lift, allowing the kite to soar. Atomizers. Devices, like perfume atomizers, use Bernoulli's principle to spray liquid. When air is forced through a narrow tube, it creates a low-pressure area that draws liquid up from a reservoir, breaking it into fine droplets.